can't remember. Yeah, Dmitri Mendeleev. Um, I know it looks like Mendeleev, but it's Mendeleev. He is considered to be the grandfather of all that is chemistry. Um, Based on what he had observed, he was able to plot, and if you look up here in this little grouping, this is his original periodic table, but he was able to predict up to 162 elements. So he and this guy Lothar were both in Germany, and they used their data and gathered different elements and put them into groups based on properties and reactivity that they would have to either water or air. And then later they gave them atomic numbers and put them into the periodic table that we see today. But this is the original, and this is Dmitri. And we will refer to him quite a bit, so let's keep going. You'll have to mind my crazy handwriting. Okay, the basic introduction to the periodic table. There are rows and columns. Rows go side to side, columns go up and down. An element is identified by its chemical symbol, which is the lettering on it, as well as its atomic number. So these two things help us identify what the element is. The number above the symbol is called the atomic number, and the number below it, traditionally, is the bigger number, and this is the atomic weight or atomic mass. Most of the time, they have a scientific notation of 3 decimal points. Sometimes you'll see them rounded up. The rows, the ones that go side to side, are called periods. And if you look down here in the bottom, I have, this is like my little cheat that I've used. I don't remember who showed it to me. It may have been Mr. Torino's. But the period, if you write a sentence, you write from left to right along a line, like a flat line. And the period goes at the end. And then group is column, and its P of group gives us the P for period. So here's just a periodic table broken into groups and periods. We don't really refer to looking at their period as far as reactivity. Their period has to do more with electrons and the shells or orbital clouds that they carry. The groups tend to lend more to its reactivity or how it reacts with things. So across the periodic table of periods are arranged horizontally. They have numbers from 1 to 7. They're arranged horizontally, so they go from left to right, but we view them as this is period 1. So this is hydrogen and helium. These elements have the same number in their valence shells, and we're going to look at that in just a second. Well, no, we'll probably look at that in a couple days. But valence shells become important when we look at how things bond. So on your periodic table, you should have taken a black or dark gray, either crayon or matte pencil, and added this stair step onto your periodic table. And it starts under boron, and it goes under boron, against silicon, under silicon, next to astatine, under astatine, next to beryllium, under beryllium, next to arsenic, no, antimony, under antimony. This breaks up our metals, which are everything from this kind of light pink over to the dark pink and the yellow. These are all the metals. And then this stair step and over to the right give us our nonmetals. So then you should have colored your periodic table. Similar to this one, we've added some different things, like this is blue in general, and then this grouping here, this period here, this group here from lithium down to francium is all red. So if you need to pause this, pause it and make your colors, and then you'll need to label them either as a key down here like I've done, like the picture shows, or as we did in class where you write them above these numbers. So then let's look at some notable families on our periodic table. Number 1, which is this first group here. It's group 1. It has a little 1A underneath it. This is our alkali metals. These are super reactive to water. They are going to want to try to bond or group up with these halogens over here. So group 1 and group 17 are going to try to bond because they want to add up to 18. The alkali earth metals, which is group 2, those are similarly reactive, but not quite as reactive. They're a little more stable in water. They tend to rust faster. These transition metals are usually where, if you were to build something out of metal, it's found here. Electrical wiring is found from in here. And then the halogens, these are sometimes heated and made into gases, which is, if you've ever heard of a halogen lamp or a halogen light, it's usually made from gases within this grouping here. And in the noble gases, these are considered full octets, which means their outer shell is completely full and they cannot accept any new electrons. So they usually do not bond with anything. So then this is a quick breakdown. So alkali metals is group 1. They react heavily with water. Some of them are violent reactions, and they bond with group 17. Alkali earth metals react, but not as much. They usually just tend to varnish or look like they're rusting. And they tend to bond with group 16. Halogens need only one electron to complete their outer shell, and they are reactive in that they try to, when they're heated, they become reactive. And then the noble gases, this is group 18, they're non-reactive and they have a complete outer shell. So looking down the periodic table, down, the vertical groups are called families. They're also sometimes called a group, but they're arranged vertically, which means up and down. And they are groups 1 through 18. This is the grouping here, 1 through 18. They have the same number of electrons in their outermost valence shell. So periods had the same number of shells. Families or groups have the same number of electrons. Oop. So here's a quick summary. If you need to pause it to write down some stuff, you may need to do that. The periodic table is a building block of all matter. Everything that's in the world can be found in its combinations on the periodic table. There are 3 main types of them. You should have gotten this in 6th grade. There's metals, metalloids, and nonmetals. Then there's these other ones that are main and transition, lanthanides, and anticides. Those are types of metals, but we don't really look at those. We just usually look, is it a metal, a nonmetal, or a metalloid? Families are in the same column and have similar properties with similar valence electrons, and those are alkaline earth, halogens, and noble gases. And then your periods are elements in the same row, have the same number of valence electrons on the outer shell. These react very similar. Keep going up there, it's not there. Okay. Some characteristics of metals. So here's where we get into the, is it a metal or a non-metal? Big 4 traits to help you decide if it's a metal. Is it conductive? Does it move either heat or electricity? Is it malleable, meaning can I pound it or mold it into shapes or sheets of metal? Is it ductile? Ductile just means can I pull it into a wire if you think about an air duct. And then does it have luster? Is it shiny? Metals tend to be hard and rigid except for mercury. This is the only one at room temperature that becomes a liquid. So here's some examples of metals with wires, engines, and then some sculptures. Malleability and ductile. If it is malleable and ductile, that means it's workable, which means I can move it into different shapes of whatever I want to be. This is where it gets hammered into thin sheets, which means I can then make it into stuff like table legs or sides of a car. They do this without breaking, and then they can be drawn into a fine wire. That's that ductile. Conductors. If you look at cooking material, your cooking pot that you make like macaroni and cheese out of is not made out of plastic. It has to be made out of metal because it needs to transmit heat to the water and not melt or bend or break. So they tend to make these out of our transition metals because they're good thermal conductors, which means they move heat easily. Uh, Electrical conductors allow electricity to pass without losing that electric current. So if you have heard last summer in the news, people stealing copper was really on the rise, because copper is a really good electrical conductor because it moves the electricity through the wiring without losing the electrons that make up electricity. Luster, fancy word for shiny. Most of us like things that are shiny and pretty, but luster is the ability to reflect high amounts of incandescent or like natural light. So this piece of metal sculpture is reflecting the sky and all the people because it's made out of metal. This is the interior of a cooking pot, and if you look, you can see kind of the X pattern, which is just how the light is reflected back off of it. So here's some more examples of metals, which you can stop and look at. Alloy is when there's two or more metals combined together. So this is like if you watch the Olympics and they have bronze medaling, bronze is made of copper and zinc combined. The bronze statues, these are actually in Dallas. You can go look at them. They're at the sculpture garden across from the DMA, the Dallas Museum of Art. They're made out of bronze, which is copper and tin. Sorry, brass is copper and zinc. Bronze is copper and tin, so they get kind of this neat patina where they turn kind of a greenish color. Brass, if you're a brass player and you don't clean your instrument properly, you know that sometimes it can tarnish and turn kind of a green color. That's the oxidation of the metals. And then here's some gas valves that are also made out of brass, which is copper and zinc. So what are metalloids? This is that stair step from a couple slides back. The boron, silicon, germanium, astatine, lead, and beryllium. This one adds lead to it. This is arsenic and antimony have some kind of shiny or luster ability to them. So they do have a property of a metal, but they are not they don't have the ability to be drawn into wires or pounded into sheets. So because they have properties of metals and nonmetals, that's what this blue scribbly writing is, properties of metals and nonmetals, they get classified as a metalloid because they are not a true metal. If you look down here at the bottom, many of these are used in semiconductors, which means they allow energy, either heat or electricity, to pass through with a little bit of energy lost, but not enough. This is what's found in your phone and your computer. It allows the phone's electricity to move around in the compartment without burning up your hand. So here's some examples of some metalloids. Silicon is used in rubber, which is used to make skateboard wheels. Arsenic, this is what arsenic looks like in its normal form, but it's also found in soap and caulking, the white stuff around your bathtub. Sometimes it can be put into glass to give it kind of a green tint. And then here is a circuit board inside of a phone, and you can see all the bits. The plastic is usually made of a silicone base because it doesn't melt under a little bit of heat. And then this green part here is called the circuit board. So there's lots of pieces that go into making up this thing. Boron, the top one, element number 5, this is a cleaning product. Germanium is used in batteries and little tiny light bulbs, and then beryllium is used in batteries and car batteries. So nonmetals, I'm going to speed this up. It's our last one. Nonmetals, they're low density, which means the molecules are very loosely packed together. They're poor conductors, which means they either lose a lot of energy by heat, or they let out electricity too fast. They do, however, make good insulators. So if you look at like a coffee cup, the styrofoam ones are considered better insulators because they have air pockets in them which trap the heat inside. If they're a solid, they tend to be brittle and with low luster, meaning they're not very shiny. All of these can be found in a solid, liquid, or gas, but most are a gas in their normal state, or they're like